And I was running far away. Would I run off the wall someday? Nobody knows. Nobody knows.
Right now, somewhere 400 kilometers above your head, an astronaut's brain is physically changing shape inside their skull. Not metaphorically, not eventually. Right now, while you're reading this sentence, their brain tissue is shifting, their fluid is rising, and their skull is filling with pressure that was never meant to be there. It sounds like science fiction, but it's real.
NASA has studied this for over a decade through what's called the Twin Study, where astronaut Scott Kelly spent nearly a year in space, while his identical twin brother, Mark, stayed on Earth. Same DNA, same starting point, completely different bodies by the end. What researchers found didn't just surprise them, it worried them. Because the greatest danger of deep space travel isn't radiation, or isolation, or distance alone. It's what all three do together to the 3 pounds of tissue that make you who you are. By the end of this video, you'll understand why some scientists believe the human brain was never meant to leave Earth at all.
Let's start with something simple. Gravity. On Earth, gravity pulls fluid downward, into your legs, into your feet. That's just how the human body has worked for millions of years of evolution. Every vein, every valve, every muscle in your legs is built around one assumption: fluid falls down. In space, that assumption breaks. There is no down. So the fluid in an astronaut's body does something it was never designed to do. It rises. It pools in the head and chest instead of the legs, almost immediately after launch. Astronauts call the result puffy face syndrome. Their faces swell within the first 24 hours. Their sinuses feel permanently blocked, like a cold that refuses to end. It sounds almost funny until you understand what's happening underneath the skin. That extra fluid doesn't just sit harmlessly in the face. It pushes against the brain itself, adding pressure inside a skull that has nowhere to expand. It flattens the back of the eyeball, physically changing its shape. It swells the optic nerve, the very cable carrying visual signals from eye to brain. NASA has a clinical name for this now: spaceflight associated neuroocular syndrome, or SANS. About 70% of astronauts on long missions develop some form of it. That's not a rare side effect, that's the majority. Some never fully recover their vision, even years after landing back on Earth. Think of it like a garden hose left kinked under a heavy box for months. Even after you finally remove the box and straighten the hose out, the material remembers the bend. It never quite returns to its original shape. And this is just the beginning. Here on Earth, our atmosphere and magnetic field absorb almost all dangerous cosmic radiation before it ever reaches us. We walk around every single day, completely unaware of the invisible war being fought over our heads, protected by an invisible shield we never think about. Astronauts don't get that protection. In deep space, there is no shield. Cosmic rays, high-energy particles moving at nearly the speed of light, pass straight through spacecraft walls like they aren't even there. They pass straight through skulls. They pass straight through neurons, the delicate cells that store your memories, your personality, everything that makes you, you. Think of the brain like a dense, ancient forest, millions of trees packed close together. Each radiation particle is a bullet fired blindly through that forest. Most of the trees survive the first shot, but every tree it actually hits doesn't heal like a scraped knee. It's damaged permanently, and it never regrows the way it once was. Studies on mice exposed to simulated cosmic radiation showed measurable memory loss, slower reaction times, and structural damage to neurons, changes that closely mirror early-stage dementia in humans. The mice performed worse on basic learning tasks. Their brains showed physical inflammation under the microscope, months after exposure. Scientists believe the same likely happens in human astronauts, but there's no ethical way to confirm it in advance. You can't deliberately damage a human brain to study the results. So researchers wait. They only find out for certain after astronauts come home, through scans, memory tests, and follow-up studies that stretch on for years. While the radiation works silently, something equally dramatic is happening at the same time to the fluid pressure from Chapter 1. The two problems don't happen separately, they happen together, compounding each other, inside the same skull at the same time. But the worst part hasn't come yet.
MRI scans from NASA's long-duration studies revealed something even the researchers didn't expect going in. After extended missions, astronauts' brains don't just get irritated by fluid pressure, they physically move. Brain tissue shifts upward inside the skull, compressed by the same rising fluid described earlier. And the ventricles, the fluid-filled cavities deep inside the brain, expand outward to make room for the extra pressure, like a balloon slowly inflating in a space that was never meant to hold it. In some astronauts, those ventricles were still measurably enlarged a full year after landing back on Earth. Not days, not weeks, a full year, with the astronaut walking around, working, living a normal life, while their brain quietly worked to repair itself from the inside. Think of it like a sponge left underwater for months at the bottom of a pool. It swells, it softens, its structure changes at a cellular level. And even after you finally pull it out and let it dry in the sun for weeks, it never quite snaps back to its exact original shape. Something about it stays different, permanently. Astronauts describe the resulting sensation as a kind of persistent mental fog, difficulty concentrating on simple tasks that used to feel automatic, trouble recalling basic words mid-sentence for weeks after they're already home and resting. Some describe it as feeling like their own mind belongs to someone else, temporarily. Nobody knows for certain whether these changes become permanent on missions longer than a year, because no human has ever attempted one. The longest continuous spaceflight in history is just under 438 days. Scientists simply don't have data beyond that point, which is exactly the length of time a one-way trip to Mars would require, minimum. While the brain is being physically reshaped by fluid and radiation, something equally strange is happening to an astronaut's sense of direction, one most people never think about until it's gone. Your inner ear contains tiny fluid-filled structures called the vestibular system, constantly telling your brain which way is up. On Earth, this system works instantly and automatically, every second of your life. You never consciously think about it. You just know, instinctively, without effort. In space, that system breaks down almost completely. There is no up. The inner ear keeps sending signals exactly like it does on Earth, but the signals no longer correspond to anything real. The brain receives confused, contradictory information from every direction at once, and the result is severe disorientation, nausea, and vertigo that can last for days after arriving in orbit. Nearly 70% of astronauts experience this so-called space adaptation syndrome during their first few days in orbit. Some can barely function. Some can't tell which way their own body is facing without looking directly at a fixed object. Think of it like a compass placed next to an extremely powerful magnet. The needle still moves. It still tries desperately to point somewhere, anywhere, but the direction it settles on is no longer real, no longer trustworthy, no matter how confidently it points. Even after astronauts eventually adapt to weightlessness, usually within a week or two, the problem doesn't disappear completely. It just relocates to a different moment in time. When they return to Earth, their brains have to relearn gravity all over again, as if experiencing it for the very first time. Some astronauts can't walk in a straight line for days after landing. Some fall over simply trying to stand up unassisted from a chair. Test pilots, some of the most physically capable humans on the planet, have needed help walking to a waiting vehicle minutes after their capsule touched down. And here is where it gets truly terrifying.
Most people assume the danger to the brain in space comes only from the brain itself: fluid pressure, radiation, disorientation. But there's a fourth threat, one that starts somewhere else entirely: the heart. In weightlessness, the heart no longer has to work against gravity to pump blood upward to the brain. Over months, it adapts to this easier workload. It becomes smaller, weaker. Studies show astronaut hearts can lose measurable mass and pumping strength during long missions, reshaping themselves into a rounder, less efficient form. That might not sound like a brain problem, but the brain depends entirely on a steady, reliable supply of oxygenated blood delivered by that very same weakened heart every single second of every single day. When astronauts return to Earth, gravity demands its due immediately. The heart suddenly has to pump against resistance it hasn't faced in months. Many astronauts experience what's called orthostatic intolerance. Their blood pressure drops sharply the moment they try to stand, starving the brain of oxygen for a few critical seconds. Think of it like a weightlifter who stops training for a year and then immediately attempts their old maximum lift.
The muscle memory is there, the desire is there, but the strength simply isn't, and something gives way under the sudden strain. For a brain already swollen from fluid pressure, already carrying radiation damage, already struggling with disrupted balance signals, a sudden drop in oxygen delivery is not a minor inconvenience. Some astronauts faint completely within moments of standing after landing, collapsing before flight surgeons can even reach them. 4 separate systems: fluid pressure, radiation, balance, blood supply, all failing at once, all interconnected, all converging on the exact same 3 pounds of tissue. But this is only the beginning of what a Mars-length mission would demand.
Radiation, fluid pressure, disrupted balance, and reduced blood flow all attack the brain physically. But isolation attacks it psychologically. And in some ways, that danger may be even greater than all the others combined. On a mission to Mars, communication delays with Earth stretch up to 24 minutes each way, depending on the planet's positions. No phone calls, no real conversations back and forth, the way humans have always communicated with each other. Just messages sent into silence, waiting for a reply that takes nearly 50 minutes round trip, best case scenario. Antarctic researchers are the closest thing scientists have to a real-world analog for this kind of isolation. Even they, with rescue technically still possible and internet access still available, report anxiety, insomnia, and a documented medical condition called winter over syndrome, memory problems, mood instability, symptoms that begin after just a few months of extreme isolation and darkness. A Mars mission would multiply that isolation by years in an environment with zero chance of rescue at all under any circumstances. No emergency flight home, no nearby hospital, no fresh supply ship arriving next week. Just the crew, the silence, the delayed messages, and their own increasingly fragile minds, trapped together in a metal container for up to 3 years. Think of it like being lost at sea, but with the added knowledge that no ship will ever come looking, and the shoreline you left behind is now nearly 225 million kilometers away at its farthest point. A brain that is swelling from fluid pressure, a brain that is losing healthy tissue to radiation, a brain that no longer trusts its own sense of direction, a brain fighting for consistent blood flow from a weakened heart. And now, on top of everything else, a mind left completely alone with itself for up to 3 years, with absolutely no way home if anything goes wrong. What scientists discovered next changed how many of them think about Mars missions entirely.
Here's the part that should genuinely concern you. Everything described so far comes from missions lasting at most around a year, mostly aboard the International Space Station, orbiting just 400 kilometers from Earth, protected partially by our planet's magnetic field. A Mars mission means roughly 6 to 9 months of transit each way in deep space, fully exposed to cosmic radiation with none of that protection, plus potentially over a year on the Martian surface itself. That's a minimum of 2 to 3 years, far beyond any duration humans have ever tested. NASA's own researchers have openly stated they don't yet know where the true safety limits are. Current radiation exposure guidelines are based on models and extrapolations, not direct long-term human data, because that data simply doesn't exist yet. Nobody has lived through it. Some scientists have proposed potential countermeasures: exercise regimens to protect the heart and bones, medications to reduce fluid pressure in the skull, artificial gravity through spacecraft rotation to trick the body into thinking it's still on Earth. Every one of these ideas remains theoretical, unproven at the scale and duration a real Mars mission would require, which means the first humans to attempt this journey won't just be explorers. They'll be the experiment itself, in real time, with their own brains as the dataset, and no way to know the true outcome until it's already happened to them.
Scientists still don't know exactly where the line is. How much can the human brain actually take before space changes it permanently in ways that can never be reversed? NASA is racing to find out through more studies, more long-duration missions, more data pulled from astronauts willing to risk their own minds for the answer. But here's the question nobody else can answer for you. If your brain might change permanently in ways doctors don't fully understand yet, would you still get on that rocket? Comment yes or no.